Now, the way in which the dark matter is distributed in that halo, there's a very precise way in which we expect it to be distributed. The type of dark matter that exists in the universe, we believe it's what we call cold dark matter, and all that means is that it's moving slowly. Under the idea of dark matter, of cold dark matter, you expect the dark matter in the central regions, you expect it to be centrally peaked. You expect there to be a lot of dark matter in the central regions and not so much in the outer regions. The density falls off as you move outwards. So we can look at a certain type of galaxy that we call dwarf galaxies and determine how the dark matter is distributed. The reason we look at dwarf galaxies in this case is because they are the easiest to analyze, because they are dominated by dark matter at all radii, and the visible matter is an even smaller percentage. I said 10% before, but for a dwarf galaxy, it's even smaller than that. So you can essentially ignore the visible matter, or if you don't get the amount of visible matter quite right, it's not that important. And then you can once again look at how fast the stars are moving around the center. That's these gray lines here. And if you subtract from that the effect that the visible mass has, then you get these black lines. That's just the dark matter. That's the idea here. The black dots here, that's just the effect from the dark matter. If it was just the dark matter, that would be the velocities that the stars would have. And then you can fit all sorts of models to these black dots and find out which one actually best fits the data that you have. Now the cold dark matter prediction, this cuspy density, the one that has a centrally concentrated density, that doesn't quite fit the data perfectly. It overestimates the velocities in the central regions right here and underestimates them here. The best fit turns out to be this magenta line, which actually has a constant density, and it doesn't become a centrally peaked in the center. You don't have as much dark matter in the center as we would expect from the expectations of cold dark matter. However, if we go to our nearest neighbor, the Andromeda galaxy, in this case, this best fitting model here, which includes things like the black hole and the stars and the dark matter, will contribute to this total velocity curve here. Then the best fitting velocity curve is consistent with the expectations of cold dark matter. So there's a bit of a question here. Why do some galaxies appear to be consistent with cold dark matter and others do not? We still need dark matter. It's just the type of dark matter that matters here. Matter that matters. And when you have a plot like the one I just showed previously, it's, like I said, as long as you know the speeds of the stars out to a certain radius, you can calculate the mass within that radius. And that's basically what we've just done here. We've calculated how much mass is within a certain radius as we go outwards. So this is the enclosed mass, that's what we would call it here, as a function of the distance from the center. So this is the total mass, this solid line, and we can break it down into the dark matter halo, this dot dash line, the disk component, the bulge plus black hole component, and even the hydrogen gas as well. That's what this is, this dotted line. We can determine the total mass of the Andromeda galaxy from this. It's 1 trillion times the mass of the sun. So that's how massive galaxies tend to be. That's a typical mass for a galaxy, including its dark matter. So one of the significant contributions that I've actually made to this field is indicating that you can actually use spiral structure. These are spiral galaxies. We can see the spiral structure, the spiral arms. You can use those spiral arms as a tracer of the dark matter. And this plot here, this pitch angle, basically tells you how tightly wound or how loosely wound spiral arms are. So when this number is small, you have a tightly wound spiral, and when it's high, you have a loosely wound spiral. And you can see that it's a linear function with the shear rate. So the pitch angle is dependent on this thing that we call shear rate. For shear rate, you can basically just say central mass concentration. It's the same thing. When you have a high shear rate, you have a high central mass concentration, and when you have a low shear rate, you have a low central mass concentration. So this is telling us, well, the dark matter should be more centrally concentrated here and less centrally concentrated here. And these are just a couple of galaxies that are in this plot. This one is called NGC 3456. This is its velocity curve, the speeds of the stars as a function of the distance from the center. This one continues to rise, which actually tells us that it should have a low central mass concentration, which it does have, and the spiral arms are fairly open, pitch angle of about 40 degrees. This one has a high shear, which means it has a falling rotation curve, as you can see here. This is the velocity curve, the velocity of the stars as a function of radius. It's AGC 7677, and it has fairly tightly wound spirals, so it's down here. So these are just two examples of two of the galaxies in this plot. So then you can use that, you can just use how tightly wound the spiral arms are to say something about how centrally concentrated the dark matter is in galaxies. Well, another useful thing about that is that if the dark matter, or the mass in total, if the total mass is more centrally concentrated, then it's easier for a black hole to form at the center. The more the mass is, the more centrally concentrated the mass becomes, the bigger a black hole you expect to get. And this is a result that we found last summer, that the central black hole mass, these supermassive black holes, do depend on how tightly wound the spiral structure is. So for tightly wound spirals, this point here is the Andromeda galaxy once again. It has a pitch angle of about 7 degrees or so, and it has one of the most massive black holes that we've observed, at least in local galaxies. It's more than 100 million solar masses. On the other hand, this galaxy down here is the Triangulum galaxy. It's pretty close to the Andromeda galaxy. This has pretty open spiral structure, a pitch angle of something like 43 degrees, but its black hole can be no more than 1,500 solar masses. So these are complete opposites, and they all fit on this nice curve here that is telling us that spiral galaxies that have tighter spirals will have more massive black holes, central black holes. And this falls under a project that we came up with last year called the Arkansas Galaxy Evolution Survey. And at the minute, the main goal of this project is a census of supermassive black holes in the universe. And we've just, in September last year, we received a lot of money from the Arkansas NASA office on campus right here at UALR. They gave us about $1.4 million to pursue this research.